Right, any questions?
I have a question on the lab.
Yes.
For the analysis question for number 3, it says, based on the technique and not on the actual results, which seems a more valid approach for finding the Coulomb's constant, using the slope or the average. What does it mean when it says, and not the actual results?
When we have a set of data, and from which we are finding a ratio. In a perfect world, either technique would get to the exact same answer, which would be roughly 9 billion Newton meters squared per Coulomb squared. However, there are certain eccentricities which show up in a lab. And so the question is, will one technique sort of ignore the eccentricities more than the other? I mean, they both have pros and cons to them. So I don't want, so based upon just philosophically, not based upon which one's closest to the correct answer, but based upon what philosophically seems like it would have made more sense to come out with a better answer. Is that sufficient?
Yeah.
Okay. Other questions? All right. I believe quiz next week.
I've got a question.
Oh,
Is
yeah.
the master set due on the 26th or the 28th?
I think it was the 28th.
Okay.
Confirmation? Okay. Did you want to do on the 26th? We can
No.
move it up. Okay.
I'm okay, thank you.
All right. Oh, by the way, I tested negative on the COVID test. Thumbs up. My wife was running short of breath, and it could have been just asthma attack, but we thought, well, let's just double check. So she went on Thursday to get tested, and I went on Sunday to get tested. I got my results back today. She still hasn't heard back from hers. Bureaucracy, or
You go to the same
Probably
place?
negative.
I'm going to assume. I figure if I've got it, she's got it, and vice versa. But
What happens if she tests positive and you're negative?
if she tests positive, then you'll be getting an email from me, an announcement saying, "Hey, guess what? We're going online for at least 2 weeks." What you have, Kyle? You had a question?
Did you go to the same place?
I guess I did. And yet somehow, I guess they saw my name and said, "We better speed this thing up."
Because, my brother, he has to, so he bowls in college,
Right?
and their season's right now. Well, it's pretty much all year, but, so whenever they have a tournament, they have to get tested twice
Ah,
before they can go. So, they normally, like, he goes, and he'll get his results back, and then all the other people on the bowling team will get their results back at the same time, within an hour or two.
well. I wonder about the checks. You go to the doctor and they see if you have a fever, and I'm going, what percentage of the people that don't show any symptoms at all? I mean, there seems to be inconsistency on what's considered good. I'm glad they get 2 tests though. That makes more sense.
And they all travel together, so it doesn't matter, you know.
If one's got it, they all got it.
Yeah.
All right. Away from the outside world into the world of perfection, because it only happens on the board. I have a universe here with a charge in it. and let's make it a positive charge. I stick into this another positive charge. I'll call it Q1 and Q2. What's going to happen to Q2?
It's gonna repel.
Okay. Why?
Because, light charges repel.
Yep. How does Q2 know that Q1 is there?
Electric field force, or electric field.
Yeah. So, this was a huge philosophical question. If you've seen the video, this is somewhat of a repeat. That how does one thing know another object exists? Obviously, we know other people exist because we see light bouncing off you and into our eye. Or it could just be a figment of our imagination, but we pretend that each one of us in here is real, all 20 of us. And so they made up something called the electric field. And Q2 has no idea that Q1 exists initially. All it knows is there's an electric field here. So this idea of the electric field is that Q1 is giving off something. So let's redraw my universe. I got Q1 here, and it's giving off something, which we call an electric field. And when Q2 gets popped into it, it senses that electric field with its spidey sense. And it says, I don't know what's causing this, but I feel this strong urge to go this way. So let's take a look at the three scenarios here. I have a positive charge here. I have a negative charge here, so think of this as a one-dimensional problem. And then I've got a positive and a negative. If I put a positive charge here, which way is this one going to go?
Right.
If I put a positive charge here, which way is it going to go? I put a positive charge here, which way is it going to go? In all three scenarios, it's going to go to the right, regardless of, sort of backtrack for a second. Each of these charges that are in black are giving off this electric field, and it's responding to the electric field, having no idea which one of these three scenarios is happening at that moment. And yes, I am acting like this has some sentience and is aware of its surroundings. Just go with it. So, since the electric field only depends upon a single charge, because that electric field existed before Q2 even showed up, we need a formula that accounts for that. And what we really have is that the force, the electric force, is equal to K Q1 Q2 over R squared. Since the electric field only depends upon one charge, let's get rid of one charge. So that's the force on 1 from 2. Then if I take that charge, divide by Q1, what I'm left with mathematically is KQ2 over R squared R2 hat. And this is the electric field produced by charge 2. It is a vector, thus the vector symbol. And they went through the creativity of electric field begins with the letter E. What the heck? Let's start it with the letter E. Let's use the letter E. When we get to magnetic field, they do not use that logic. So, we can write this, since we have only one subscript here, we have this, all the subscripts are the same. Is there really, and there's no other subscript, we really don't need to use it, so we can just write generically, the electric field is K, Q over R squared, R hat. So if Q is positive, my electric field is in the positive R hat direction, R hat being the radial unit vector, which points away. So if Q is positive, the electric field is going away from it. So it's going, my electric field is emanating, like this is the sun. So at this point right here, my electric field is going to the right. For a negative charge, if Q is negative, then the electric field is in the negative r hat direction, which means opposite of away, as Austin hand gestured, towards. And I will shorten the number of arrows I'm drawing. And again, at this point, it's pointing to the right. And then here, when I have two charges, it is pointing to the right because of the positive charge. It is pointing to the right because of the negative charge. So we can generalize this. We got two pieces to it. Electric field goes away from positive source and goes toward negative source. That's the first piece of trying to explain why things attract or repel using electric fields. The second piece of it, a positive charge, whatever, capital or lowercase, positive charge goes with probably in same, is forced, that's more accurate, is forced in same direction as the electric field, same direction as external electric field. It is not affected by its own electric field. Although some theorists have tried to make that claim. I guess if you had the particle traveling faster than the speed of the electric field, it could effectively be affected by itself. Well, that'd be possible. If instead of a positive charge here, I had a negative charge, it obviously would go in the opposite direction. And so the last bit is negative charge is forced opposite direction as external electric field. This has a nice advantage in the fact that I no longer really have to set up I no longer have to set up the situation. All I can say is that I have an electric field that's traveling, that is going to the right here, and I put a positive charge in it. And you now know what's going to happen. So we have two ways of describing why things attract or things repel, or we could loosen it up and just give you the electric field and the charge that's put into it, and you can then predict the behavior. This ultimately is going to lead to justification for circuits, which we'll get to for the second test, or test 1B. So let's just do a quick and dirty problem. I have a 3 nanocoulomb charge. 2 meters away. What is the electric field at this point right here? I'm going to call it point P. Well, we got our nice little formula right here. So that's 9 times 10 to the 9th. Charge is negative 3 times 10 to the negative 9 divided by the distance squared. I'll just leave it right there for right now. 6.75?
Mm-hmm.
All right, and if this were a 10-point problem and you put that down right as an answer, I knew that you know what you're doing, but I would still take off 60% of your problem for that. So what's missing?
Units.
All right, that and
The negative sign.
a little bit more than that. I'd probably take off
The
5 points if
direction.
you just included the negative sign.
The
Direction.
Yeah. There's more than, we need to do more than just put a negative sign there. All right, so first off, let's units. What are the units?
Would be newtons over coulombs.
It would be, just think back to here, newtons over coulombs. All right, and now the direction. You want to still go with a negative sign? All right. What else do we need?
R hat.
Okay. And you can get away with R hat, and there's only one reference in here, so I'm fine with just R hat here. If I had more than 1 point, I would need something more specific than just R hat. Or you could have also just said, hey, that way it's positive, and just left it at negative. In which case you're defining your coordinate system. Questions? All right. So now let's find the electric field from an infinite line of charge. With a charge density, linear charge density of lambda. Linear charge density. And a distance r away. Let's set up so that's my point P right there. I want to find the electric field at point P. And I have drawn it more neatly than that in the past. There we go. And let's just set up I have J hat. So we got two approaches here. One, we could use calculus. Or two, we could take advantage of something we did last week. What is the force? If I put a charge Q1 right here, what is the force on charge Q1? Feel free to look at your notes if you don't have it memorized.
It's 2 K Q lambda over R, big R, J hat.
All right, that's the force. How do we find the electric field if I know the force at that point?
Divided by Q1.
Yeah. We have a source here. Well, this is the force acting on the charge Q1 there. If I want to know the electric field, I just remove that charge and make it more generic. So my electric field is the force divided by the charge, which becomes just 2K lambda over R J hat. Or with the epsilon in there, this becomes K lambda over 2 pi R J hat. Oops, lost my epsilon there. 2 pi epsilon. Now, if I had not derived this last class, then I would have derived this using calculus. Calculus has to show up somewhere. Suppose I have an infinite sheet with surface charge density of, I think I used sigma last time, or did I use eta?
Sigma.
Sigma, all right. What is the electric field at this point P here? Or walk me through how to find it.
Is it 2k sigma pi?
2k sigma pi.
Pi hat?
Yeah, let's use the same convention we have over there. Or in terms of epsilon, sigma over 2 epsilon sub naught. I guess I hat in this particular case. And we'll be using that again, definitely. And then if I have a conducting sphere, of radius, we'll call this R1, and then I'll take some other point here, R2. Total charge on this is Q. What is the electric field at this distance R2?
Is it k times big Q divided by R2 squared?
If we're outside a conducting sphere with an excess charge on it, the excess charge will be on the surface and it will be spherically symmetric. If I have a spherically symmetric charge here, if I'm outside, I can treat it like a point charge right there at the center. So the electric field, K big Q over R2 squared, R hat. If I'm inside,
0.
yep. So, let's do a plot. Actually, before we get into the graphs, because everyone loves the graph, so let's just, something to look forward to. Any questions before I keep erasing? Awesome.
Are you deriving an equation here? Is that what you're like?
I'm just exploiting the equations we derived last time. If we actually derived it, we would do the exact same thing we did the last time, except not have that little q that I threw in.
Okay.
So it's a sort of a shortcut derivation using the shortcuts that we've already talked about, finding the electric field. Is that sufficient? Okay. Other questions?
What does that say?
This right here,
Yeah.
conducting sphere. or conducting sphere? I'm gonna go with the first thing. All right, so let's do a plot. I've got this R1, that's the radius right there, R1. This is my electric field. And R hat. And this is some distance R. What does the graph look like? Or can we at least graph part of it if we don't know the whole thing?
Is 0 until R1.
All right. So inside the conducting sphere, since all the charges on the outside, ultimately the force on any charge on the inside is 0, or the electric field inside it is 0. And then what happens?
As you increase the radius, the electric field will decrease. So it's inversely proportional to the distance,
All right, so inversely proportional to the distance.
the radius between, the distance from the conducting sphere to the point outside of it.
So how does that graph look?
It'll go down to the negative.
Go down as in that?
Yes.
Now we generally assume, I didn't say what Q was, but we generally assume it's positive unless otherwise stated. How would you get a negative number here if that's positive, that's squared, that's just a unit vector, and Q is a positive number? How do we get a negative?
By flipping the coordinate system.
Yeah, let's not flip the coordinate system.
Won't it be a graph of 1 over R squared?
Yeah, it's inversely proportional to R squared, by the way. So what does that look like? So where am I drawing that? First quadrant or fourth quadrant?
First.
All right. So as long as I'm outside, I treat it like a point charge, and so it is sort of like this until I get to the surface. This point right here would be KQ over R1 squared. That's that magnitude. And then we get this quick drop off here. Now, in reality, it's not a sharp peak there. There's no sharp point, despite the fact that I drew a sharp point down here and up here. But it is a very quick drop off. It would depend upon, you've got charges on the surface, they're sort of buzzing around. In reality, there'd be some curves there. But this would be basically the electric field versus the distance from the center of a charge given if it's conducting, a conducting sphere. Some of you probably already anticipated what's coming next. I now have an insulating sphere. Insulating? A sphere made of some insulator. You know what? Let's just dielectric sphere. Dielectrics are insulators. I have a dielectric sphere here with a uniform charge density. So that goes with this. Set up the graph again. We got electric field in the R hat direction versus R. I got R1 right here. So we still have this spherical symmetry. So what does the graph look like, or at least part of the graph?
Inside will always be 0.
Pardon?
The inside will always be 0.
No, that's actually,
That's just for conducting.
That's
Yeah,
just
for conducting, it's definitely zero inside, but for insulating, if, with a uniform distribution, it's not. Now, if I said that all the charge was on the outside, I would treat it like conducting one, but I didn't. Well, let's just take bits and pieces here. Suppose I'm outside the sphere. No. R1. Suppose I'm outside the sphere. What's it look like?
Should be like, the charge should be evenly applied around it, right?
The force should be evenly applied around. Is that what you said?
Well, no, it would, charge should stay where it's applied there. I don't know.
I missed a word there. Sorry.
I was saying at first that the charge should be evenly applied around it, but it being an insulator, the charge would only stay where it's applied.
Right. And I applied it evenly throughout.
Yeah. So,
Okay.
So then if you apply it evenly throughout, then won't it be the same as?
Yeah. Outside is going to look like this. Let's just go ahead. Uniform density and a total charge of Q. All right. So it should look the same as this, whether it's insulated or conducting. If I'm outside and there's spherical symmetry, I can still treat it like a point charge if I'm outside. The question is what happens inside. What about the electric field in the dead center?
Would it just be just one line, like a horizontal, it would be the exact same electric field magnitude?
A constant electric field throughout? No, it's not going to be.